Welcome to part two of this lecture on the reaction of period 3 chlorides with water. So part one deals with the ionic chlorides, sodium, magnesium, and aluminum chlorides of period 3 with water. And we find that as you go from left to the right, the ionic character decreases, the covalency increases in these molecules, and hence you find that the solutions turn more acidic. We spoke about that in depth. Now today we shall, in this lecture, we shall see about the covalent chlorides, right? The covalent chlorides are silicon and phosphorus chlorides. The covalent chlorides, as we already know, are simple molecules. So what they do is they'll actually get hydrolyzed and react very vigorously with water. So you have silicon tetrachloride getting hydrolyzed, okay, when it's added to water. So you get silicon dioxide, which is going to be a white color solid, and you will have hydrogen chloride gas produced. And we know that hydrogen chloride is seen as a misty or a steamy white fumes. Okay, steamy white fumes, you see. The hydrogen chloride produced is highly soluble in water. As a result, it dissolves in water, giving you hydrochloric acid solution, which is the reason why we say pH is around 0 to 2 for this solution. Okay. In fact, if you have a lot of water, in that case, the hydrogen chloride gas is never seen because all of it gets absorbed and dissolved in the water, just giving you the hydrochloric acid instead of the hydrogen chloride gas, but the reaction is pretty vigorous. All right, so to balance it, I'll have the 4HCl to water, and I think that does the job. Phosphorus, as we know, forms two chlorides, phosphorus 3 chloride and phosphorus 5 chloride. Okay, phosphorus trichloride, which is a liquid at room temperature, and phosphorus pentachloride, which is a solid at room temperature. We've seen that already. The oxidation number here is +3. The oxidation number here is +5. Okay, of these chlorides. Both of them react very, very vigorously with water, get hydrolyzed, producing the phosphorus-containing acids. All right, phosphorus-containing acids. This will give you H3PO3, which is called as phosphorus acid. Okay, or phosphoric 3 acid, as it's called now. And you will have here H3PO4, which contains the phosphorus in the +5 oxidation state. And this, you know, is your more common phosphoric acid, which is more correctly called phosphoric 5 acid, with the oxidation state of phosphorus being stated. Both reactions are highly vigorous. They give you misty white fumes of hydrogen chloride gas, right? Hydrogen chloride gas. But as we've said already, in both cases, if there is enough water present, you may not see the gas being given out because it dissolves off in water, producing hydrochloric acid, which is the reason for the pH of the solution being from 0 to 2. Okay, so the important things to remember are is that the ionic chlorides would dissolve in water, giving you hydrated ions in solution. Okay, while the covalent chlorides undergo hydrolysis, giving you hydrogen chloride gas and acidic solutions. And as you go from left to right, the ionic nature decreases, the covalent nature of the chlorides increases. As a result, they tend to become more hydrolyzed and tend to become more acidic. Okay, that wraps up the solution, discussion on the reaction of the period 3 chlorides with water. Okay, moving on. There's this little discussion also about the nature of the hydroxides. Okay, and the acid-base nature of the hydroxides. Okay, I don't think this is a big discussion because there are just 3 hydroxides that have been stated. One is sodium hydroxide, The other one is magnesium hydroxide. Magnesium hydroxide. And the third one is aluminum hydroxide. This is a new addition to the syllabus, right? We know that sodium hydroxide is actually strongly alkaline because it dissolves in water. Yeah, it dissolves in water. So as a result, sodium hydroxide is alkaline. Magnesium is strongly alkaline. It's got a pH of around 14. Magnesium hydroxide is not very soluble. We've covered this earlier itself in the reaction between magnesium oxide and water. All right, so magnesium hydroxide does not dissolve very well in water. So you'll actually get a white suspension. The pH of the solution is going to be somewhere around 9-ish. Okay, it's a pretty weak alkali. But aluminum hydroxide is actually insoluble in water, or sparingly soluble, as we call it in chemistry. Okay, sparingly soluble in water. However, the aluminum hydroxide does does react with both acids and alkalis. Okay, reactions are exactly the same as the reactions of the oxides with water, with acids and alkali, giving you salts in both cases, showing that aluminum hydroxide is amphoteric, right? So if I have to, let's say, if I have to put them in a table, right, I think that would be better. So let's say if I have these guys, right, say sodium hydroxide, magnesium hydroxide, and aluminum hydroxide. The bonding in all three of them is ionic, though you do understand that as you go from left to right, because the size of the cation decreasing and the charge increasing, plus the electronegativity difference is becoming lower, you are going from purely ionic or very strongly ionic to something that is decreasing in ionic nature and increasing in covalent nature. So that follows. So in this case, the solution is basically strongly alkaline. Okay, this would become weakly alkaline if it dissolves in water. While this is amphoteric, it is insoluble in water. Okay, so highly soluble in water. Okay, partially or less soluble in water. While this is insoluble or sparingly soluble, as it's called. Okay. Sparingly soluble in water. All right, as a result, the concentration of OH- ions actually keeps decreasing, leading to a decrease in your alkalinity. Okay, so it follows the same trend as that of the oxides, and that is something that you are supposed to know.